Okay. So what I'm about to show you is some very actively ongoing research. It's actually more engineering. The results that I'm going to show you are benchmarked as of last week, and there's a lot of changes going on. But I think that this might be a little peek into how we might interact with instruments, especially kind of more complex instruments that require some expertise, how we might interact with them in the future. So the prototype that I'll show you today is, also someone mentioned yesterday that they hadn't heard the word multi-agent very much at this workshop. You're about to hear it a whole lot. So this is a multi-agent, large language-driven prototype for controlling an X-ray microscope. It can do things like it can design, interact with it contextually, meaning you can use kind of domain-specific material science knowledge, and it'll do some of the lifting to convert that into like the X-ray material science knowledge. And it'll do some of the lifting to convert that into like the X-ray physics knowledge that you need to actually, operate the instrument correctly. And it can perform literature reviews to suggest acquisition parameters based on prior work that people have done. Because of the time limit, I'm going to really focus on the top two, the automatic data acquisition and analysis. I do think the contextual stuff is interesting, but I'm more excited about the data acquisition. So now I'm going to back way up because I know not everyone in the room might know, but an X-ray microscope is used, like a lot of different microscopes, for many different applications within material science characterization. It provides you a non-destructive 3D data set, which is really useful, especially for like production level analysis. You can do things like look at internal defects, you can segment phases, you can look at grain analysis, you can do in situ studies like that one over there. So a pretty wide range of applications. The way an X-ray microscope actually works is you have an X-ray source. This could be a synchrotron, or in today's case, it'll be a laboratory X-ray source. You have a sample that's sitting on a stage. The stage at least needs to rotate, but preferably also can move in X, Y, and Z. And then you have an X-ray detector. And what you do is you shine your X-rays on the sample. You get what's called a projection image. It's like a shadow going through the image. You collect a bunch of these 2D projection images at different angles, and then you can reconstruct a full 3D volume, including the internal features of the sample. And then that 3D volume, you can slice it and dice it, and use that for quantitative analysis. So here, what I'm showing you, we've segmented the internal defects from this additively manufactured lattice. We're looking at its like porosity and things like that. It's pretty rare, however, that the workflow stops here. Typically, your first acquisition is not your last acquisition. You need to do some tuning of your parameters, or you want to zoom in on a specific feature. So you do and then you do more data acquisition. And there's one particular type of, and then you do more data acquisition. And there's one particular type of workflow that I'm targeting with this automation tool. A lot of people use these systems for doing what I call process property feedback loops. It's where you're manufacturing a bunch of samples. So here, this is a study out of Oak Ridge, one of my favorite studies from recent years. They're printing a whole bunch of additively manufactured samples, and they want to study how to minimize the porosity in their effects velocity affects the power, and the print velocity affects velocity affects the porosity. So they make a whole bunch of samples, and then each individual sample needs to go through this kind of X-ray microscopy characterization loop. It could be a one-shot where you acquire data sets a couple times to get the right data. You have to kind of acquire data, you segment it, you get the porosity, right data. And then you analyze that data, you segment it, you get the porosity, and then you feed that into some kind of model. It's typically an active learning, machine learning model. And then the model results feed back into the manufacturing process. Someone made a great point yesterday that it can be somewhat easy to set up an automation for one workflow, but then it's very difficult to adapt that workflow to new samples. So people are doing this for additive, they're doing it for batteries, they're doing it for biomedical devices. And I could sit down and write you some Python codes that would script one of these workflows, but then it wouldn't work very well in the other domain. So I want a tool that can kind of handle that. So a couple things have really come together in the past year to make automation easier for these types of workflows. The vice versa X-ray microscope, it can be controlled via a Python 2.7 API, soon to be a Python 3 API. And you can do everything you'd ever want. You can move all the motors and stages, you can acquire data sets, things like that. A lot of image processing tasks can also be done via Python. There's plenty of robust open source Python modules for doing X-ray or any kind of image analysis. As we've all seen, large language models are very good at writing Python code. They can also parse user workflow or parse user instructions, but really in the past year, there's a type of, and then in the past couple years, but really in the past year, there's a type of architecture of large language model systems called a multi-agent system. And this is where you use many different large language models kind of in series or in a loop. And each individual large language model has its own task as part of the workflow that it executes. And so we're going to be using a multi-agent system today to try to automate some of these workflows. So there's a couple things I definitely need my multi-agent to be able to do, preferably 100% of the time. You know, where to put the sample or the detector, how to calculate magnification based on features, things like that. It needs to be able to analyze images, patient based on features, things like that, degree. And a bonus goal that we're going to be talking image segmentation, at least to a certain degree. And a bonus goal that we're going to be talking about today is it would be nice if the system had a long-term memory. So if it could remember previous workflows that it's developed, and then when a new user comes along, leverage that previous workflow to kind of increase the success rate. So these are kind of the minimum viable operations that I want my system to be able to do right now. So let's get into the details of how this multi-agent system actually works. It's composed of 5 different large language model instances and 1 hard-coded math module. So probably the 2 most important large language models are what I call the instrument agent and the analysis agent. The instrument agent is an expert at writing Python code specifically for the Versa X-ray microscopes, so for operating the microscope. And then the analysis agent is an expert at writing Python scripts for segmenting images and 3D tomography volumes. There's an orchestrator. This is the user entry point into the system. It's actually the one who receives the instructions and then plans a workflow, and then it delegates tasks to the instrument or the analysis agent based on what the user asks. There is a geometry module. This is not a large language model. This is a hard-coded calculator, essentially, which we'll get a little bit or RAG. This is how the system can ingest. It's called retrieval augmented generation, or RAG. This is how the system can ingest technical documents and then give suggestions to the user. It's also what enables kind of contextual domain-level speech with the instrument. We have pre-trained several of the agents on certain documents or information they might need. In particular, the instrument agent has been shown the full documentation of the API, so all the code it needs to actually operate the instrument. We've also shown it a couple example scripts that it commonly would execute. So how, this is what a script looks like for moving the stage or acquiring a 3D tomography, things like that, how to convert files, etc. For the analysis, it turns out ChatGPT is already pretty good at doing image segmentation. It's very good at writing skimage and OpenCV code. So all I really had to do to reinforce the analysis agent was I had to tell it about the various coordinate systems. We're working with about 4 different coordinate systems between various things, and this has actually been a major pain point that we're still working on. The geometry module, like I said, is a math module. This is a pro tip that I've learned from working with these things, is that if you're doing a certain operation often and you can hard code it, then you should. Anytime you use a large language model, there's a chance it messes up and produces an error. And so if you're doing this thing all the time, then you might as well hard code it. So what you're looking at here in the middle, this is a segmentation from the analysis agent, actually. It's a 2D slice through a 3D volume. We're looking at like a 3D printed block. You can see we've segmented the largest defect or pore inside the sample, and we've got a bounding box around it. We've also found its centroid. So what the geometry module does is if you give it a real space coordinate, then it will calculate where to move the stage so that that real space coordinate is on the center axis of rotation. And if you give it a feature size, if you tell it how large something is, then it will calculate where to move the source and detector to achieve a desired magnification. And this is something that I really don't want to mess up. This is like kind of the most key thing, is being able to be successful. All the Python and the agent wrote, and I've got all the workflows and the metadata and things like that. And a trick we can do is we can use an LLM, workflows and the metadata, take these input response pairs, we can embed them into a vector space, in such a way that input response pairs, we can embed them into a vector space in such a way that semantic response pairs, we can embed them into a vector space in such a way that semantically similar tasks are embedded to a vector space in such a way that semantically similar tasks are embedded together. So in this example, if you look, words like all the fruits are kind of clustered together in this embedding space, and woman and queen and king and man have, they're near each other because there's some kind of semantic similarity. So the idea is that similar tasks that the user has run should be embedded in a similar area of this vector space. Then, when a new user comes along, we take their input, we embed it into the same vector space, and we look and see, is there anything nearby? Essentially, has anyone run any workflows similar to this one? And if they have, then maybe showing those examples to the agents will improve their success. And we're going to be testing whether or not it actually does later. And so we take those prior successes and we show them to the agents before they start doing their thing, and hopefully they get some inspiration on how to do it correctly. This slide is a little in the weeds, so I'm not going to go too in depth. The main thing that you should take away from this is outdated. It is no longer state of the art. If you're going to start working with these multi-agent systems, the number one thing you should remember is to use structured outputs and use the model context protocol. Okay, so protocol, and it'll make your system just work a whole lot better. Rigorous, so I actually want to benchmark how well is this that I wanted it to do, but I want to be somewhat rigorous, so I actually want to benchmark how well is the system performing on these types of tasks. So be somewhat rigorous, so I actually want to benchmark how well is the system performing on these types of tasks. So I've developed two kind of initial benchmark tasks that I want to test how well it's doing. The first one is I want it to be able to center the sample on the axis of rotation so that we get a nice centered 3D data set. We'll go a little bit deeper into the actual workflows. And then slightly more complicated workflow is what we call a scout and zoom. So in this one, we're going to take an initial move to a magnification of, send the sample and find its centroid, and then we're going to tell it move to a magnification of, some magnification, configure the instrument into this new magnification setting, and then reacquire a data set, and we're going to see, did it move to the correct magnification? So let's actually jump into those benchmarking tests. So the first one, as I said, is 2D axis of rotation centering. The first thing we're going to do is we're going to move the sample to a random position on the stage. So you'll notice it's not in the center of the image at the moment. We need to take an initial image, segment that image, and find the centroid of the sample. We're just looking at a block of Inconel right now. We then need to calculate where to move the stage so that the sample is centered on the axis of rotation, move the stage to the new position, and then take another image. So in a successful workflow, we start with our sample out of the center on the left, and then we move it into the center of the image. And we want to test, okay, if we use that memory retrieval, does it improve our success? So if we show it prior successes, does it actually improve the performance? So I'm going to be showing you plots like this, and let me get to the laser pointer. So the y-axis here is telling you how many LLM calls or how many messages did I have to send throughout the entire workflow, right, that executed correctly. How many Python handle these errors? They wrote a Python script that did not execute correctly. This is okay. We can actually handle these errors pretty gracefully. Not execute correctly. This is okay. We can actually handle these errors pretty gracefully. Gray means that the orchestrator decided to update the workflow. Gray means that the orchestrator decided to update the workflow after it had already decided on an initial workflow, and then at some midpoint it said, hey, let's actually change and do something else. That's not a bad thing necessarily. Sometimes that's a good thing, but we don't want it to do too much changing of the workflow. And then there's a certain amount of overhead. So this is just like basic message passing, which again isn't bad, but we don't want too much overhead. So here's an example of like one of these 2D centering workflows. This did work correctly. It took about 2 minutes. Here are 10 random samples from this 2D centering workflow. And you can see there are some cases where we're writing wrong, incorrect Python scripts initially, but the agents can be shown what was wrong with that Python script and then write a new one and try again. And so actually all 10 of these were successes. Here is a sample of 10 random initial conditions on the left and then 10 final positions on the right. You will notice there are some slight differences in the final position. There were also some things that I didn't tell the multi-agent what to choose. Like I didn't tell it what image binning to use. I didn't tell it what acquisition times to use. So it kind of chose randomly in the final state. So there are some inconsistencies, but it's working at least. In the case of memory retrieval, so on the left, we have 20 random samples without memory retrieval. And then on the right, we have 20 random samples from this task with memory retrieval. There's not a lot of difference. There are some common errors between two. The main one is the x-rays did not turn on, which is actually, and Zeiss will hate me for saying this, that's our issue, it's an API issue, it's not one with the multi-agent. And then saving and opening files is also sometimes an issue for reasons I won't get into. So I do want to say though, all 20 of these that you're seeing on both sides, these were successes. So the sample did a mean workflow. So we're going to start with the sample on a printed block. We're going to start with the sample in the same condition every time, and then we're going to start with the sample in the same condition every time, and then we're going to take an initial 3D tomography, the sample in the same condition every time, and then we're going to check. And then we want it to acquire a second data set at those new conditions. And then we're going to check, okay, did it move to the want it to acquire a second data set at those new conditions. And then we're going to check, okay, did it move to the right magnification set at those new conditions. And then we're going to check, okay, did it move to the right magnification. So without, and then we're going to check, okay, did it move to the right magnification. So without using memory retrieval to the right magnification. So without using memory retrieval, these are 10 random samples of this task. The ones that you see with the red circle above it, that means the workflow did not complete. Either the orchestrator chose to quit the workflow, which is something they can do, or the user had to step in and say, whoa, 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 like you're going crazy, and stop it manually. We did have a couple full successes, meaning it did get to the final position, and a couple what I call partial failures. Some of the common errors, like I said, incorrect file naming is a big issue with these multi-agents. The segmentation is not, I haven't given it a lot of context, like I said, so it does fail on the segmentation and analysis tasks. In some case, it doesn't find a sample at all. And another major issue I have is getting it to use the right coordinate systems. Because if it doesn't, then the geometry calculations are kind of useless after that. However, this was one case where we saw that memory retrieval had a major performance on improving the system performance. So here we have 9 full successes. You'll see that one under number 8. Even though there were a couple Python scripts that didn't execute correctly, ultimately the workflow worked. We had one case where it kind of fell into this like long iterative loop of writing the wrong Python file. But then after I intervened and I said, hey, the file that you're looking for is saved here, then it finished the rest of the workflow pretty correctly. So, you know, if you're wondering, okay, how well does this thing actually work? I would say, here's kind of a taxonomy, initial proof of concept to here, successes in just a few weeks. Here's kind of a taxonomy of some of the successes and failures. So here's kind of a taxonomy of some of the successes and failures. So in a successful scout and zoom, you know, we said, okay, take up 40% of the field of view, and then, you know, the sample does take up 40% of the field of view, or take up 50%. Some of the partial failures is the sample, you'll notice, is not centered on the axis of rotation, and then in some other cases, you know, the acquisition parameters it chose were just bad. Now let's move. I put defects inside of them intentionally, and I basically combined the two, and I put defects inside of them intentionally, and I combined the two previous workflows inside of them intentionally, and I combined the two previous workflows. I said, hey, center each sample on the axis of rotation, and then do the magnification step, segment the data sets, and then tell me which one has the most pores and which one has the largest pore. And it will do the workflow, meaning all of the acquisitions will complete, but we're still having some issues with getting the segmentation and analysis to be up to the level that we want. So this is kind of where we're at currently with the benchmarking. Now I just want to give you some kind of thoughts that I have about these multi-agent systems. These multi-agents I wouldn't call them a method in and of themselves. I would call them a glue between other interfaces and APIs. They're a really nice, easy to set up glue. However, you must have a well-supported API. If you don't, you can't expect the multi-agent to do anything useful. Excuse me. Some of the further advancements that we're currently working on are maybe pretty obvious. So we've got a working prototype for an X-ray microscope. Now let's do an optical microscope. Now let's do an electron microscope. And we've got some prototypes for those instruments as well. If you're working on these multi-agent systems, there's a tendency to kind of like be like, oh, it seems it works, and then keep going on. I really recommend you develop these benchmarks and these taxonomy of tasks, because they will help you in debugging and figuring out what's actually wrong with the system. And finally, a topic that's been talked about, so on the very well documented. All the Python scripts you wrote, all the parameters you chose, the whole workflow is very well documented. All the Python scripts you wrote, all the parameters you chose, they're saved right there with the Python scripts you wrote, all the parameters you chose, they're saved right there with the multi-agent. On the other hand, these multi-agents are being used for something called vibe coding, which is essentially someone is using a multi-agent to write code that they don't understand. And that's fine if you're building like an iPhone app, but for science, I think that's a problem. And on the one hand, I think there's a cultural aspect of we need to be skeptics and we need to doubt the things that the multi-agent is doing. But also I think maybe, and this is my personal opinion, is on the vendor side, maybe we need to prevent the type almost entirely, and got it to this point in about 6 months. The agent, these are some of the educational resources that I highly recommend entirely, and got it to this point in about 6 months. So these are some of the educational resources that I highly recommend you check out if you're interested. So these are some of the educational resources that I highly recommend you check out if you're interested. In particular, this YouTube channel, I don't know this guy, but he has an incredible YouTube channel that's very useful for this type of thing. And finally, I just want to say, you know, I have a lot of access to instruments, but I don't have access to real samples. So if you're at a university or a national lab and you have a good use case where you would, like a high throughput workflow in your hands, test out this multi-agent system, please come talk to me, because I'd love to put it in your hands, and maybe we could publish a paper together using the system. So thank you all so much for your attention, and I'll take any questions if we have time.